So if you guys would, I'll turn to page 12. Let's take a look at page 12. I'm gonna make this a little bigger for the guys in the building. And make it bigger for you guys at home. Boom. All right. So last time we dealt with solving for molality. So if we take a look, molality is moles over kilograms of solvent. So if we have 0.45 moles and we have 4.45 kilograms, we want moles over kilograms. That's how we set it up.
Good morning, North Central. This is Mrs. Horn, Assistant Principal. I want to thank everyone for their cooperation today during our monthly fire drill. These drills are practice so we can ensure your safety and security in the event of an actual fire. Thank you very much. I hope everyone has a great Panther Day.
So if we take a look, we put that in there, we get 0.1. The problem is it's just not correct answer significant digit wise. So if we take a look here, I have 1, 2, 3 significant digits, and here I have 1, 2, and 3. So the least number of significant digits out of both of these is 3. How many significant digits does this have? 1. Very good. So in order to make this 3, I need to add a 0 and a 0. These zeros, since they're to the right of the decimal place and terminating, this one is terminating. That is significant. And this 0, since it is between a significant digit and another significant digit, it is significant as well. Cuckoo. So colligative properties. We are going to discuss boiling point and freezing point. But colligative properties are properties that depend on the amount of stuff solute dissolved in a solution. So if we take, for example, water, actually, let's change this. Let's say put in a solvent. Sorry, I'm going to change that to solvent. We take water. Water is our solvent. We actually said that water is known as a universal solvent. If we take, we know that water uses hydrogen bonding to kind of hold on to itself. Water has a decently high boiling point. What's the boiling point of water? What temperature does water start to boil at? Pure water. I'll take Fahrenheit or Celsius for this. Nobody. I'll even let you type it into the chat. I'll look at the chat. You can type it into the chat. 212 degrees Fahrenheit. Can anybody give me that in Celsius? It's easier in Celsius. Nice round number. Hundred. Water boils at 100 degrees Celsius. The particles themselves hold on to each other through hydrogen bonding. And only whenever we get those particles moving fast enough at 100 degrees Celsius do we start to get boiling. Then the particles start flying off of each other. But if we have salt or some other substance dissolved into there, that's going to get in the way of those particles from flying off of each other. So the boiling point will be elevated. Elevated means it's higher. So we have the colligative property for water. Its boiling point, whenever more particles are dissolved in it, the boiling point goes up. The formula for that is delta T B equals the index or the von Hoff factor times the molality times the K of B. So what does the delta mean? Remember last semester during thermodynamics, we talked about delta meaning something? Well, what's the normal boiling point? 100 degrees. So if we want to find the new boiling point, what do we need to find? What's the delta temperature of boiling? Change.
My bad. I just woke up late.
All right, thanks, Ka. This is the change in boiling. K always means constant. So K is constant. For water, K sub B equals 0.512 degrees Celsius per molality. I is the index, also known as the von Hoff factor. Basically, what that means is whenever a ionic compound dissolves, like sodium chloride, you get two particles. So the index here would equal 2. We know that this is an ionic compound because it starts with a metal. If it's not an ionic compound, for example, C12H22O11, C is not a metal. This does not separate, so its Van Hoff factor is 1. Remember, it's the amount of particles of solute dissolved in a solvent. So the index, for every 1 mole of this, it's actually 2 moles of particles. For every 1 mole of this, it's only 1 mole of particles. I don't know why I put 2 for that. Sorry about that. My brain got stuck for a second. So the index, the Van Hoff factor is 1 for that. So what is lowercase m? Well, that is molality. For non-electrolytes, I is equal to 1. Because of dissociation of ionic compounds, you actually get more moles of ions in solution. So 1 mole of NaCl breaks down into 1 mole of Na and 1 mole of Cl. So the Van Hoff factor is 2. 1 mole of Na2S and it breaks down into 2 moles of Na and 1 mole of S. So the Van Hoff factor here is 3. Here we have 3 NAs and 1 PO4. That's the hardest thing for people to see. That is 1 polyatomic ion. So we add 3 plus 1 for that, we get 4. Okay, good. So if 168 grams of sodium phosphate is dissolved in 2.50 kilograms of H2O, what is the boiling point? The normal boiling point of H2O is 100 degrees Celsius. So we are going to have to add the delta T sub B to that. That will equal our new boiling point. So delta T sub B equals IM K sub B, where K sub B is 0.512. 0.512. If you don't know where I got that, it's a constant, so I have to have that memorized or find it somewhere. I'll write it on the back of my periodic table. Degrees Celsius per molal. What is the molality? Well, that's what I don't know. So I need to change this 168 grams and 2.50 kilograms to molality. Every 1 mole of sodium phosphate, 22.99 times 3 plus 16 times 4 plus 30.97.
That would be 163.94.
163.94 grams. I got that by adding up all these from the periodic table, right? 16 times 4, 30.97, 22.99 times 3. That's going to allow me to convert from grams to moles. 168 divided by 2.5 divided by 163.94.
The answer is about 0.4099.
So that will have 3 significant digits, and the units will be molality, because grams cancel out and I get moles per kilogram. That's what I'm going to put right here. Keeping in mind, I'm only going to use 3 significant digits of it. My Van Hoff factor, Na3PO4. What is my Van Hoff factor for that? Is sodium a metal? It's 4, good. It's 4. Sodium is a metal, so we have 3 from sodium and 1 from PO4. So then we're going to take 4 times 0.4099 times 0.512.
The answer is about 0.8394.
And we're going to add, right? We said that had 3 significant digits. So we're going to add that to 100. We're going to use 100 exactly because that's the boiling point of water. The boiling point of water is based off of, I'm sorry, 100 degrees Celsius is based off of the boiling point of water. That's how they set that up. So when I add this to this, notice that molarity cancels out, or molality cancels out, leaving me with degrees Celsius. So I get 100.839 degrees Celsius. Let's talk about freezing point. It's the same thing, except for freezing point goes down. So we call this freezing point depression. The formula for this is exactly the same. The K of F, if I remember correctly, it's 1.86. Yep, 1.86. So it is depressed. Now, why would the freezing point go down? Well, basically, we have salt dissolved in water. Let's imagine that, for example, sodium chloride dissolved in water. When water freezes, its particles start to reorganize and crystallize. And if salt's in the way of this crystallization, it's going to have to get lower in order for it to reorganize better. So whenever you have a solvent, the freezing point goes down. Now, what is the freezing point of pure water? I'll accept Fahrenheit or Celsius to start with. 32 degrees Fahrenheit. Problem is our constant here is in degrees Celsius. Can anybody tell me the freezing point of water in Celsius? 0. So the whole thing for the Celsius scale is it's based on water. At 0 degrees, water freezes. At 100 degrees, water boils. Just keep that in mind. So here's our example. The molar freezing point depression constant for water is 1.86. We got that? Predict the freezing point of a 3.60 molar aqueous glucose solution. So notice this is glucose. Glucose, do you remember C12H22O6 from your biology days? I'm sorry, that's sucrose. C6H12O11 is glucose. So if we take a look, is this a metal? Carbon? Is carbon a metal? So if you recall this little line right here, that separates our metals and non-metals. Is carbon on the metal side or the non-metal side of that line? Non-metal side, right? These are skills that you guys should have acquired by now. So this is, you got to be able to look at that and say carbon, not a metal. You have the periodic table in front of you always, but the fact that it's not a metal means that these do not separate and the Van Hoff factor is 1. So I go back to my formula. Delta Kf equals ImKf. The Van Hoff factor is 1. The molality is 3.6. The K of F is 1.86 degrees Celsius per molal. Again, notice that the molality cancels out. 1 times 3.6 times 1.86.
The answer is 6.696.
So if we take a look, this 1 is infinite in significant digits. Each of these have 3. This is a perfect number. Each of these have 3. So we need to round this to 3. Then when we add, we'll have to go out 2 decimal places. In this case, we're actually not adding, we are subtracting because the boiling point or the freezing point is depressed. So we take 0 degrees Celsius minus 6.70, which equals negative 6.70 degrees Celsius. So if you had this much sugar water, this many molal sugar water, then it would take you to get down to this temperature before it would start freezing. This is good to know. We know that certain systems, for example, one of the things we know, we put salt on the roads to prevent it from freezing in the wintertime. Our cars, we have a glycol, is it actually in here? Yeah, ethylene glycol. Ethylene glycol is known as antifreeze. So we put that in our car's engine on our radiator to make sure that we prevent that from freezing up and the engine breaking. All of these different things we use throughout our lives are based on these theories. So I will try one more, and then I will let you guys do the rest for homework. So I'm going to solve for this one down here. It says that sodium chloride can prevent water from freezing as low as negative 21.1 degrees Celsius. What would the molality of this have to be? So we know that the change in temperature freezing is equal to I m K of F. Well, how much does that change? Well, that was subtracted from 0 to get negative 21.1. So that right there, that 21.1 degrees Celsius, that is my change. What's the Van Hoff factor for sodium chloride? Well, what's the formula for sodium chloride? What's the symbol for sodium? Na. What's the symbol for chlorine? Cl. What's the charge of sodium? No, the charge. It's the charge of sodium. 1, right there, right? What's the charge of chlorine? -1. So that means that this formula for sodium chloride is NaCl. So that means my Van Hoff factor, since sodium is a metal, my Van Hoff factor is 2, since I have one of each of these. What is my molality? Well, as the problem says, that is what I want to figure out. What is the Kf? That is this constant, 1.86 degrees Celsius per mole. So what I need to do is I need to divide both sides by 2 and both sides by 1.86 degrees Celsius per mole. 21.1 divided by 2 divided by 1.86.
The answer is about 5.672.
Notice degrees Celsius cancel out. We have 1 over molality, which means that will be the inverse of the inverse, which will be the normal. And we get 5.67. That means that at negative 21.1 degrees Celsius, the maximum molarity that you could have of salt would be 5.67 moles per kilogram. Molality, sorry, not molarity, molality. Moles per kilogram. 5.67 moles per kilogram of solvent. So there you go. Your homework for tomorrow is 1, 2, and 3. 1, 2, and 3. Questions about that? So the top one, what are you trying to find? And what are you trying to find in the top one here? Number 1, an aqueous solution of sucrose boils at 112 degrees Celsius. What are we trying to solve for?
I'm trying to find the molality.
All right. And do you remember what the molality is? That's moles per what?
Moles per. It's on the tip of my tongue. It's the God, hold on. It has to do with the periodic table. Is the mass of the
solvent, right? And you don't need a periodic table for that. That should be given to you. The mass of the solvent
Okay.
for everything we're doing, the solvent we're using is H2O.
Okay.
So that's what you're trying to find for there. Or we would keep in mind that that is in the formula here as lowercase m. Number 2, we are trying to find the what?
The freezing point of the
Freezing
solution.
point. And number 3, we are trying to again find the molality.
Yeah.
Good, good. So you have problems 1, 2, and 3 for tomorrow. Please make sure that you do those. And if you have some stuff missing on Canvas, make sure that you get that done. My goal today is to switch that over to Skyward. Then that calls will be going out pretty soon by the end of the week, guys. Have a great day.